Welcome viewers. In this video we will see the effect of load on a synchronous motor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Synchronous motor. In that, effect of load. What happens if the load is applied in the synchronous motor? Refer the diagram. There are two diagrams available. Diagram A, diagram B. Diagram B is torque angle at no load. Here we are referring the torque angle. So this is the torque angle, right? So here is at there is no load. This is the rotor and part of the stator is available. This is the axis. This is the rotation of the stator flux. At the no load condition, the flux is uniformly distributed between the stator and rotor. There is no load in this diagram refers torque angle at no load. This is diagram B. Torque angle at rated load. Load is applied. So what happened? So there is a angle is formed. This is the angle, torque angle. Delta is the torque angle, and see the fluxes are as going in a direction. Here it is uniformly distributed. Here it is go through one side. It is going through a one side. It's not uniformly distributed. This is based on this distribution of the flux, the angle is formed, that is delta. So the rotation of the stator flux. So this diagram B refers torque angle at rated load. This diagram A refers at no load. Here at loaded condition. So this is the torque angle delta. Now we'll see the equation, voltage equation based on this no load as well as rated load. What is the effect of this? Due to that, what happened in the equation, this EMF equation. I will see the detail one by one. So we need to refer the diagram A and diagram B. Diagram A refers no load condition. Diagram B refers rated load. When the motor is on no load, the position of stator and rotor pole is as shown in the diagram A, that is uniformly distributed. The fluxes are uniformly distributed between stator and rotor. At this condition, the induced EMF is equal to the applied voltage. Both are equal. Induced EMF is equal to applied voltage, that is V phase equal to EB plus IA ZS. What is this V phase? This is V phase, this is the back EMF. What is this IA ZS? At no load, the motor intake is 0. So the losses IA ZS is 0. So this is refer the loss. At no load condition, there is no intake. So there is no loss. This term is 0. So that we got V phase equal to EB. Both are equal. But it is opposite. EB is opposite to V according to Lenz's law. Right? So this is the general equation. In that, due to no load condition, the loss is 0. So V phase equal to EB. Both are equal, but based on the Lenz's law, it is opposing each other. So based on that, the vector diagram is given. So it's EB and B phase. See that both are in opposite direction. This is going this side, this is going that side. So the resultant voltage ER equal to V phase minus EB, that is equal to IA ZS equal to 0. Right? So both are equal and opposite, so it becomes 0. This is referring the no load condition. No load condition. This vector diagram also refers the no load condition. So during no load condition, the losses is 0. V phase equal to EB, but it is in opposite direction. So finally the resultant is difference between these two, that is loss, that is equal to 0. Now we will refer the loaded condition. Now when the motor is loaded, it slow down momentarily to adjust itself to change in load condition. So when it is loaded, what happens? The speed is slowly slightly decreases in order to maintain the load condition. So the rotor pole fall back from the stator poles by an angle of delta as shown in the diagram B. So in the diagram B we already referred, the stator post, the rotating rotation of stator flux is going one direction, one-sided. Based on that direction, the angle delta is formed. We refer the torque angle delta, right? In the diagram A, it is uniformly distributed. Now it is fall back to one side. Del is the called as torque angle or load angle or coupling angle or angle of retardation, right? So the delta we already referred. It may be, we can say that is a torque angle or load angle or coupling angle or angle of retardation. Now we'll see what is the effect due to this load. The magnetic locking will be still exist between stator and rotor poles, but the magnetic flux lines will be stretched due to the load angle delta. So there is a locking between stator and rotor poles. The fluxes locking. In diagram A, uniformly distributed, but here it is stretched on one side, that we already refer in the diagram B. But in both the cases, locking is available. That is given here. Locking is available. Now though EB equal to V phase, but EB will not be exact phase opposition to each other. So in the first case, no load condition, we refer that both are equal and opposite. But here it's not opposite, exactly not in phase opposition to each other. But the EMF EB will be displaced by an angle delta from the initial position. So this due to this delta, this EMF is displaced by an angle delta. This delta we already referred, that is a torque angle. So based on that, the phasor diagram is now available. So this is V phase and this is EB. So this is displayed by an angle of delta. In the first case, both are in same line. Both are equal and opposite. Now it is displaced by an angle of delta. So this is due to the load effect, torque angle delta. The sum of these two is nothing but resultant. Vector sum of EB and V phase is the resultant voltage, that is Ia Zs. In previous case, Ia Zs is also 0. So now these two vector sum is ER. So that based on that we can frame the equation. The vector difference between V phase and EB is called resultant voltage ER. ER equal to V phase minus EB, that is equal to Ia Zs. In previous case it is 0. This loss is 0 and these two are both are equal and opposite, that also 0. Now not equal, both are not equal, it is displaced with an angle of delta. So we can frame this equation. The load angle del increases with the increase in load. So when the load increases, the angle also increases. So that is the observation we got from this analysis. When the load is increases, the del also increases, that is the fluxes are stretched on one side. If it is no load, uniformly distributed between stator and rotor, while loading stretched on one side, based on that the angle delta is formed. So the delta will increase with increase in the load. So in this video we discuss the effect of load on a synchronous motor. We discuss the diagram A, diagram B. Diagram A refers no loaded condition, diagram B refers loaded condition. So there is an angle of delta is there. We observe that delta will increases with increase in load. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. All the best for your examination.